All right, welcome to this explainer. Today, we are going to completely demystify the fundamental rules governing exactly how the entire universe operates. If you've ever found yourself wondering why things happen the way they do, whether that's on a cosmic scale, a macroscopic scale, or deep down at the microscopic level, you are in exactly the right place. Let's get into it.
We're going to start with a bit of a mystery. Think about it. Why do observable things like water flowing or iron rusting only naturally happen in one specific direction? Like, why does water enthusiastically rush down a mountainside but absolutely requires a pump and external energy to go back up? Or why does a shiny car bumper rust over time, but that rust never just magically reassembles itself back into pristine metal? Well, it all comes down to a crucial concept called spontaneity.
So here's our roadmap to figure this out. 1. The mystery of spontaneity. 2. Entropy and hidden microstates. 3. Laws of the universe. 4. The power of free energy. And finally, 5. The big picture.
The mystery of spontaneity.
Okay, so in thermodynamics, a spontaneous process simply means it occurs naturally under certain conditions. But honestly, the word spontaneous can be incredibly misleading if we mix it up with how we use it in everyday conversation. For instance, did you know diamonds are actually converting into graphite literally right now? It's true. Because of the extreme pressures under which they were formed, diamonds are actually less stable than graphite at room temperature. The process is fully spontaneous, meaning it needs absolutely zero outside energy to happen, but the rate is so incredibly slow that it creates the illusion that it's not happening at all.
And this brings us to a really crucial distinction. Thermodynamics simply asks, will it happen? Kinetics, on the other hand, asks, how fast will it happen? A spontaneous change might be instantaneous, like a massive explosion, or it could be like the decay of uranium-238, which has a half-life of over 4 billion years. So remember this, spontaneity has absolutely zero correlation with speed.
Part 2. Entropy and hidden microstates. To really grasp why these spontaneous changes occur at all, we have to zoom way in on the microscopic world. If energy doesn't necessarily drive these changes, because, some spontaneous changes absorb energy while others release it, what is the universal driving force? The answer is entropy. Now, the crucial point here is that entropy isn't just disorder. We always hear it described as chaos or a messy bedroom, but mathematically and physically, it is fundamentally about how matter and energy spread out. It's about the dispersal of a system's matter and energy.
Picture this. If you open a valve between two flasks, the gas inside naturally rushes to fill both, right? It does this because a more uniform dispersal of matter is simply the highly probable outcome. The molecules were previously confined to a small space. By opening that valve, we increase the available volume, and the gas spreads out. But why is this dispersed state so likely to happen on its own?
Well, Ludwig Boltzmann actually gave us the exact math for this. He proved that the state with the greatest number of possible microscopic arrangements, what we call microstates, has the highest probability, and therefore the highest entropy. Think of it like rolling a pair of dice. Rolling a 7 is the most probable outcome because there are simply more combinations, or microstates, that add up to 7 than any other number. In a gas, a state where particles are evenly distributed has exponentially more possible arrangements than a weird state where all the particles decide to huddle up in one corner.
We actually see this in everyday life all the time. As a solid block of ice melts into liquid water and then boils into a gas, the particles gain massive freedom of motion. In the ice, they're locked into a rigid structure with very few possible arrangements. But when it melts, they flow over one another. Boom, more microstates, more entropy. And when it becomes vapor, they can fly literally anywhere in the room. The dispersal of matter radically increases.
Part 3. Laws of the universe.
Now that we have a microscopic grip on entropy, let's scale it up to the cosmic level. I want you to think of the universe as an incredibly strict accountant that is constantly balancing the entropy changes of a specific system against its vast surroundings. See, sometimes a system loses entropy, like water freezing into a highly ordered, rigid ice crystal. But that freezing process actually releases heat into the surroundings, which agitates the surrounding air molecules and increases their entropy. The universe's ledger always combines both of these things.
And this brings us to the profound second law of thermodynamics. For any process to happen naturally, the net entropy on the universe's ledger absolutely must go up. Even if a specific little system becomes perfectly organized and tidy, it has to expel enough heat or energy to make the surrounding universe messier by a much greater amount. The total sum has to be a positive increase in entropy, no exceptions.
When we actually calculate the universe's entropy for melting ice, we see that at higher temperatures, the heat absorbed from the surroundings still results in a net positive entropy for the universe. That's what drives the spontaneous melt. For example, at 10 degrees Celsius, the entropy gained by the water turning into a liquid is greater than the entropy lost by the air cooling down. The net universe entropy increases by plus 0.9 joules per Kelvin. That positive number? That's basically a green light from the universe saying, yep, this is going to happen.
Conversely, the third law of thermodynamics establishes our absolute baseline. At absolute zero, 0 Kelvin, a perfect crystal has absolutely no motion. 0. That means there's only one possible microstate, and therefore exactly 0 entropy. This is the ultimate ground floor. If we plug that single microstate into Boltzmann's equation, the natural log of 1 is 0. It is literally the only theoretical scenario where a system possesses no entropy at all.
Part 4. The power of free energy.
So, as you can probably guess, calculating the entropy of the entire universe's infinite surroundings every single time we want to know if a reaction will happen is practically impossible. It's incredibly tedious. We desperately needed a cheat code. Introduced by Josiah Willard Gibbs, this incredible concept of free energy allows us to predict if a reaction will happen just by looking at the system itself. By combining the internal energy changes with the entropy changes of the system, Gibbs gave us a single mathematical variable to act as our ultimate predictor.
And here it is. The equation perfectly captures the balance. The free energy is simply the difference between the energy produced by a process and the energy inevitably lost to entropy, leaving us with what is actually available to do useful work. Think of it exactly like a paycheck. Delta H is your gross income. T times delta S, that's the universe's unavoidable entropy tax. Delta G is your take-home pay. It's the energy actually free and available to power a car engine, a lithium battery, or your own body cells.
The sign of delta G is our ultimate indicator. If it's less than 0, meaning it's negative, the process is spontaneous and will absolutely happen on its own. It's like a ball rolling downhill. If delta G is positive, the process is non-spontaneous, meaning you physically have to push that ball up the hill by doing work on the system. And if delta G is exactly 0, then the system is just perfectly balanced at equilibrium.
Part 5. The big picture.
Okay, we've covered a ton of ground, but the way these concepts interlock is literally the foundation of all chemistry and physics. Here is the universe's rulebook. 1. Spontaneity is driven by matter and energy dispersing. 2. The universe demands a net positive entropy. 3. Free energy, or delta G, acts as our ultimate predictor for useful work. We've journeyed from the macroscopic illusion of speed, down to the probability of microstates, out to the universal ledger of the second law, and finally to the practical predictive power of free energy. Spontaneity isn't magic, and it sure isn't speed. It's just the cold, hard mathematical probability of matter and energy naturally seeking their most dispersed state.
So I want to leave you with one final, massive thought to chew on today. If these unbreakable rules dictate that the universe is constantly moving toward maximum dispersal and maximum entropy, what is the ultimate fate of reality itself? As the universe expands, as stars burn out and release their heat, we are steadily marching toward a state of maximum microstates. It's pretty wild to realize that the exact same rules allowing us to live, breathe, and do work right now are the very rules slowly dispersing the entire cosmos. Thank you so much for joining me on this explainer, and keep questioning the universe around you.